Welcome to clickmyprojects.com. Multi-level on-chip CAD systems have been widely adopted in high-performance multiprocessor. To keep data consistent throughout the memory hierarchy, write-through and write-back policies are commonly employed. Under write-back policy, a modified cache block is copied back to its corresponding low-level cache only when the block is about to be replaced. While under the write-through policy, all copies of the cache block are adapted immediately after the cache block is modified at the current cache, even though policy maintains identical data copies at all levels of the cache hierarchy throughout most of their lifetime of execution. This feature is important for CMOS technology is scaled into the nanometer issue in on-chip cache system. Consider a two-level cache system. For example, if the L1 data cache implements the write-back policy, a write hit in the L1 cache does not need to access the L2 cache. In contrast, if the L2 cache is write-through, then both L1 and L2 caches need to be accessed for every write operations. Obviously, the write-through policy ensures more write access in the L2 cache, which in turn increases the energy consumption of the cache system. Power dissipation is now considered as one of the critical issues in cache design. In this paper, we extend this work by making the following contribution. First, a detailed VLSI architecture of the proposed weight tag cache is developed, where various design issues regarding time, control logic, operating mechanisms, and area overhead have been studied. Second, we demonstrate that the idea of weight tagging can be extended to many existing low-power cache design techniques, so the better trade-off of performance and energy efficiency can be achieved. Third, a detailed energy model is developed to quantify the effectiveness of the proposed technique. Finally, a comprehensive suite of simulations is performed with new results, the effectiveness of the proposed techniques under different cache configurations. It is also shown that the proposed technique can be integrated with existing low-power cache design techniques to further improve energy efficiency. Here, we propose a Veta cache that exploits the way information in L2 cache to improve energy efficiency. We consider a conventional set of associative cache system when the L1 cache loads or writes data from or into the L2 cache. Always in the L2 caches are activated simultaneously for performance consideration at the cost of energy over. Now I am going to explain the flow diagram of our project. In the first step, we get an input address from CPU and fed at the initial stage to L1 cache memory. From the L1 cache memory, the input address was given to write buffer. Write buffer is a buffer register which collects the informations from L1 cache memory. This contains the location informations which are as mentioned as here index to create a path to L2 cache memory. From the write buffer, we extract the addresses and fed to path buffer. In this path buffer, it collects the informations which are locations in data arrays in L2 cache memory. Then these addresses are given to MUC to extract the multiplexer output from L1 cache memory, which are addressed from write buffer memory and the internal L1 cache address. Then this address was fed to L2 cache memory. At the initial stage of L2 cache memory, it extracts the address from L1 and check the request which are write enables or read enables option. Then from that extract, it checks the indexes which are matching to data arrays from tag array. From the tag array, it collects the informations which are the data located in data arrays and extract the particular data arrays which are mentioned in the tag arrays by using the label datas. Then from the data arrays, it checks the updated informations and relocate it into memories from CPU and to the secondary memories and internal memories also. Without write buffer, we can't extract the particular informations from the data arrays and it checks the overall data arrays from the database. This will extract more time consumption and will also extract the power consumption also. So, with the help of write buffer, we can minimize the total timings level and reduce the power losses made by L2 cache memory. Now I am going to explain running procedure of our project. In the first stage, we check the syntax error, which our programming language done any errors or warnings, which will be displayed in the console window. Then also we view the RTL schematic diagram and technology schematic diagram. So for that process, we first select the implementation option and select the main function and click check syntax and run it. In this, it checks each and every lines in the codings and displays the errors or warnings which are made in our coding. It will be displayed in the console window. So it will generate the log files which are providing any errors or warnings which will be displayed in the design summary. And we can view the RTL schematic diagrams by run the view RTL schematic. The RTL schematic will generate the logical circuits and designs which are provided as in the coding language. Here we are using BSD coding language. The synthesizers will generate the HDL synthesis reports. Now click add and click create schematic. This is our overall schematic diagrams. In this, the inputs are address inputs, RAM data, clock, enable, L1 write and read. Then it gives the address out, RAM out. This is our internal structure of RTL schematic diagram. We can view the technology schematic by run view technology schematic. And click add and click create schematic. We can view the internal circuit of technology. This will display the LUTs and flip-flop structure of our proposed work. Now I am going to explain the timing diagrams of our project. For that process, select simulation and select the main function and run simulation model. This will provide the timing diagrams guide window. Here we are using iSim simulator to display the timing diagrams of our project. It will display the internal structures, signals and input and output pins outputs. Now I give the clock input as set to 0 at the initial stage and gives the address input. This address input is set as address from CPU. Then I give the RAM data address. This is the data address which are going to updation. Then I give the enable as set to 1 and L1 write as set to 1. Read is set to 1. Click the run option. Now change the clock cycle. So this initial case, for each and every cases of clock period, it will be generated as 0. States will be changed. Now I change the reading option as set to 0 and run the clock periods at one iteration. One iterations of clock representing one cycle. That means one negative on the clock, positive clock periods. This will display another state. So now I varies the clock cycle. So for each and every clock cycles, it extracts the frame outputs, which are generated from the page allocations from L1 and L2 caches. Finally, this will be displayed in the address data outputs. So for each and every iterations, the state level will be varies for according to the clock variation. At the last stage, we extract the address output, which are fed from given L2 cache array. This will be matched result from L2 array and finally fed at the address output. It is fit to memory addresses to store or write or read the data which are fed as in initial states. Thank you.